When we look at the Earth, it often seems like a calm and motionless world. Mountains stand firm, oceans roll with their waves, and the fields appear green and unchanging. But the truth is, our planet is alive on the inside, and its heart is constantly beating. This heartbeat comes from plate tectonics, the extreme heat in Earth's core, and the constant movement of molten rock beneath the crust. And the Yellowstone supervolcano is one of the most powerful signs of this living planet's pulse. Yellowstone sits on what scientists call a hotspot, a place where an extremely hot plume of magma rises from deep within the mantle toward the Earth's surface. This magma melts the crust above it, creating an enormous underground heat source. The size of this hotspot is astonishing. Through advanced seismic imaging, researchers have discovered that beneath Yellowstone are two massive magma chambers. The first chamber is about 55 miles long, 18 miles wide, and several miles deep, containing a mixture of solid and molten rock. Beneath it lies an even larger and hotter chamber, stretching deeper into the mantle. The amount of heat and pressure stored within this system is enough that, if released all at once, it could cause one of the largest natural disasters in human history. The difference between a supervolcano and a regular volcano comes down to size and energy. A regular volcano might eject ash and lava over a few miles, but a supervolcano can release over 1,000 cubic kilometers of material into the atmosphere. The eruption of a supervolcano is so powerful that its effects can be felt from one continent to another. In Yellowstone's case, scientific models suggest that such an eruption could reshape land hundreds of miles away and alter weather patterns across the globe. Scientists monitor this sleeping giant using a range of tools. Seismometers record even the tiniest earthquakes. Yellowstone experiences between 1,000 and 3,000 small quakes each year, most of them too weak to be felt, but all reminders that something is moving deep below. GPS stations track minuscule changes in the land's surface, even shifts as small as a few millimeters, to detect whether the ground is rising or sinking, a sign that magma might be building up or shifting. Gas sensors measure levels of sulfur dioxide and carbon dioxide in the air, because a sudden increase in these gases can indicate growing volcanic activity. The stages of a volcanic eruption can be broken into 4 general phases. In the first phase, pressure builds in the magma chamber, and tiny cracks begin to form in the crust. In the second phase, earthquakes become more frequent, and hot springs and geysers become more active. In the third phase, the pressure reaches its breaking point, part of the crust shatters, releasing an explosion of lava, ash, rocks, and gas into the atmosphere. The fourth phase, which can last weeks or even months, is a period of lava flows and falling ash, until the pressure finally drops and the system goes quiet again, sometimes for centuries, sometimes for just a few thousand years. Scientists at Yellowstone say there is currently no evidence that an eruption is imminent. However, they closely watch every minor change deep underground. This constant monitoring is important not only for the people living nearby, but for the entire world, because a supervolcano's effects are felt on a global scale. The fact that Yellowstone is both a national park and an active supervolcano makes it a unique natural laboratory. Here, scientists can study the movement of heat beneath the crust, measure the flow of magma, and better understand how our planet works from the inside out. Yellowstone is a reminder that we live on a restless, dynamic planet, one that can surprise us at any moment. The story of Yellowstone's past is written not in books, but in layers of ash and rock that stretch across hundreds of miles. Geologists believe the Yellowstone hotspot has been active for at least 16 million years, leaving a trail of massive volcanic scars across the western United States. The land that is now Idaho, Nevada, and Oregon bears evidence of older eruptions, each one marking where the North American tectonic plate slowly drifted over the fixed hotspot, like a conveyor belt passing over a blowtorch. The most important part of Yellowstone's volcanic history is its 3 giant eruptions, each one so large that it is classified as a supereruption. The first took place about 2.08 million years ago, creating the massive Huckleberry Ridge Tuff, a layer of volcanic rock spread across much of the region. That eruption left behind a caldera, a giant crater formed when the ground collapses after magma is emptied from beneath it, stretching more than 50 miles. The second supereruption occurred 1.3 million years ago, producing the Mesa Falls Tuff. Although smaller than the first, it was still enormous by normal volcanic standards, ejecting hundreds of cubic kilometers of ash into the atmosphere. This ash fell as far away as the Gulf of Mexico and covered parts of what are now Iowa, Nebraska, and Kansas in a layer several inches thick. The most recent and perhaps most famous eruption happened about 631,000 years ago. This was the event that formed the Yellowstone caldera we see today, a depression 30 miles wide and 45 miles long. During this eruption, more than 1,000 cubic kilometers of rock and ash were thrown into the air. Ash clouds darkened skies across North America, and a blanket of volcanic debris fell over much of the continent. The eruption was so powerful that it altered landscapes for thousands of miles and may have influenced global climate patterns for years afterward. But Yellowstone has not been silent since then. Over the last 631,000 years, the region has experienced dozens of smaller eruptions, most of them involving lava flows rather than explosive ash clouds. The most recent lava flow occurred about 70,000 years ago, creating a thick layer of rhyolite rock still visible in parts of the park. And while these smaller eruptions were far less destructive than the supereruptions, they are reminders that Yellowstone's volcanic system is still active. Native American tribes have known about Yellowstone's geothermal activity for thousands of years. Long before European settlers arrived, tribes like the Shoshone, Crow, and Bannock visited the area for its hot springs, geysers, and abundant wildlife. Some oral traditions describe the land as sacred and powerful, a place where the earth's spirit is close to the surface. European exploration of the Yellowstone region began in the early 1800s, but many early reports of boiling springs and steaming rivers were met with skepticism back east. It wasn't until the Hayden Geological Survey of 1871 that the region's wonders were fully documented, leading to Yellowstone's designation as the first national park in the world in 1872. But even then, the full scale of the supervolcano beneath the park remained a mystery for more than a century. It was only in the late 20th century, with advances in geology, seismology, and satellite mapping, that scientists began to realize the immense size of Yellowstone's magma system. Studies revealed that the park sits atop one of the largest reservoirs of molten rock on the planet, and that it has the potential to erupt with a force unmatched by any modern volcano. This historical record, from ancient supereruptions to modern geothermal activity, shapes how scientists think about Yellowstone today. It tells us that while supereruptions are rare, they do happen, and the forces that drive them are still alive beneath our feet. The past is not just history here, it is a warning, written in stone. Today, Yellowstone is one of the most closely monitored volcanic systems on Earth. A network of more than seismographs, GPS stations, tiltmeters, and gas sensors constantly feeds data to scientists at the Yellowstone Volcano Observatory, YVO, a joint program run by the U.S. Geological Survey, the University of Utah, and the National Park Service. Every tiny earthquake, every bulge in the ground, every change in hot spring chemistry is recorded, analyzed, and compared to decades of historical data. According to Dr. Michael Pollan, the current scientist in charge at YVO, there's no evidence that a supereruption is imminent. We would expect to see significant warning signs years in advance, he explains, including intense earthquake swarms, rapid ground deformation, and major changes in gas emissions. In other words, Yellowstone is not a ticking time bomb ready to explode without notice. It is a complex and active geological system, but one that gives clues long before a major event. Satellite radar has shown that the ground within the Yellowstone caldera can rise and fall by several inches over the course of months or years. This breathing is caused by the movement of magma and hydrothermal fluids beneath the surface. While dramatic sounding, these movements are a normal part of Yellowstone's life cycle. In fact, ground uplift has been observed multiple times over the last century without leading to an eruption. Earthquake swarms, groups of hundreds or even thousands of small quakes occurring in a short period, are another common feature of Yellowstone. Most are too small to be felt, but they are closely studied because they can indicate the movement of magma or hot water underground. The largest recorded swarm in recent history occurred in 1985, with more than 3,000 quakes in 3 months. None of them triggered an eruption, but they helped scientists better understand how Yellowstone's plumbing system works. Gas emissions are also a key part of monitoring. Volcanic gases, especially carbon dioxide and sulfur dioxide, escape through vents and hot springs. By measuring these gases, scientists can estimate how much magma is close to the surface. Elevated gas levels could be a warning sign, but so far, Yellowstone's emissions remain within its historical range. Despite the reassurance from experts, the scale of Yellowstone's past eruptions means it will always be a subject of public fascination and occasional fear. Some researchers, like Dr. Jacob Lowenstern, former head of YVO, emphasize that while a supereruption is possible in the distant future, the yearly probability is extremely low, estimated at about 1 in 730,000. For comparison, that's much lower than the odds of being struck by a large asteroid in your lifetime. Instead, scientists say the more likely hazards from Yellowstone in our lifetime are smaller eruptions of lava or hydrothermal explosions, violent steam blasts that occur when superheated water comes into contact with shallow magma or hot rock. These explosions can send rocks and boiling water hundreds of feet into the air, damaging areas within the park but having little impact beyond it. Modern monitoring has turned Yellowstone into one of the best understood volcanic systems in the world. And yet, as Dr. Poland notes, nature still has surprises. Our job is to be vigilant, to understand the signals, and to communicate them clearly to the public. The balance between scientific vigilance and public perception is delicate. Too little information and people might ignore real warnings, too much hype and unnecessary panic can spread. In the end, the experts agree on one thing: Yellowstone will erupt again someday. It may not be in our lifetime, or even in the next 1,000 years, but the forces beneath the park are still very much alive. The only question is when, and in what form, the Earth will choose to remind us of its power. If the Yellowstone supervolcano were to erupt in a catastrophic event, the impact on the United States would be unlike anything in recorded history. While the likelihood of such a supereruption is extremely low, understanding the potential consequences helps illustrate why Yellowstone is studied so closely. The immediate area surrounding Yellowstone, primarily parts of Wyoming, Montana, and Idaho, would face the most severe devastation. Within a radius of about 50 miles 80 kilometers from the eruption center, pyroclastic flows, superheated clouds of gas, ash, and volcanic rock, could sweep across the landscape at speeds exceeding 200 miles per hour. Temperatures in these flows can reach over 1,000 degrees Fahrenheit, incinerating nearly everything in their path. Towns like West Yellowstone, Gardiner, and Cody would be obliterated in minutes. Beyond the blast zone, the next major hazard would be volcanic ashfall. This is not the soft ash from a fireplace, but a dense, abrasive mixture of rock particles and glass shards. Depending on wind patterns at the time of eruption, ash could blanket much of the continental United States. The heaviest deposits, several feet thick, could bury cities in the surrounding states, collapse roofs, destroy crops, and clog rivers. Even a few inches of ash can disable vehicles, short-circuit power systems, and contaminate water supplies. Models created by the U.S. Geological Survey suggest that in a worst-case scenario, states as far away as Nebraska, Kansas, and Oklahoma could see ash accumulations of several inches, while the East Coast might experience a thin dusting. Air travel across North America would likely be grounded for weeks or even months due to the danger volcanic ash poses to jet engines. The environmental impact would be global. An eruption of this magnitude would eject hundreds of millions of tons of sulfur dioxide into the stratosphere. There, the gas would combine with water to form sulfuric acid aerosols, which reflect sunlight and cause temporary cooling of the Earth's surface. This phenomenon, known as a volcanic winter, could lower global temperatures by several degrees for years. Crops could fail across multiple continents, triggering food shortages and economic instability. In the United States, agriculture in the Midwest, the nation's breadbasket, could suffer devastating losses. Reduced sunlight, cooler temperatures, and disrupted rainfall patterns would make growing seasons shorter and yields much lower. Livestock could also be affected as pastures become covered in ash, forcing farmers to rely on stored feed, which could quickly run out. Infrastructure damage would extend far beyond the immediate region. Ash particles are highly abrasive and can destroy turbines in power plants, grind machinery to a halt, and infiltrate electronics. Electrical grids could fail, and water treatment plants might be overwhelmed. The cleanup effort in major cities could take years, and in some areas, relocation might be the only option. Public health would face a crisis. Volcanic ash is dangerous to breathe, especially for people with respiratory issues. Hospitals could become overwhelmed with cases of volcanic ash inhalation, eye injuries, and other related health problems. Masks and air filtration systems would become as essential as food and water. Psychological and social impacts would also be profound. Millions might be forced to evacuate permanently from affected zones. Entire communities could vanish from the map. The economic cost could exceed anything the United States has ever faced, possibly reaching into the tens of trillions of dollars over time. While this all sounds apocalyptic, scientists emphasize that this is the absolute worst-case scenario, and far more likely as a smaller-scale eruption or hydrothermal explosion. But these models are important because they help the government and emergency agencies prepare. By studying Yellowstone's geography, understanding wind patterns, and simulating various eruption sizes, scientists and policymakers can develop response plans aimed at saving as many lives as possible. Ultimately, Yellowstone's potential reminds us of two things. The United States sits atop an incredibly dynamic planet, and our modern society, for all its technology and infrastructure, is still vulnerable to the raw forces of nature. Yellowstone is not just a breathtaking national park filled with geysers, hot springs, and wildlife. Beneath its serene beauty lies one of the most complex and potentially dangerous volcanic systems on Earth. To understand its present and prepare for its future, we must look into its past. Geological evidence shows that Yellowstone has experienced 3 massive supereruptions over the last 2.1 million years. The first, about 2.08 million years ago, created the Huckleberry Ridge Tuff and formed a caldera over 50 miles wide. The second, around 1.3 million years ago, produced the Mesa Falls Tuff, a smaller but still massive eruption. The most recent, about 631,000 years ago, was responsible for the Lava Creek Tuff and the present-day Yellowstone caldera. Each of these events released thousands of cubic kilometers of volcanic material, enough to blanket much of North America in ash. However, not all volcanic activity at Yellowstone has been catastrophic. In fact, since the last supereruption, there have been dozens of smaller lava flows and hydrothermal explosions, the most recent lava flow occurring around 70,000 years ago. These smaller events show that the system is still active but not necessarily on the brink of another supereruption. Scientists have reconstructed these ancient eruptions by studying ash layers buried in the soil, volcanic deposits across the continent, and the chemical composition of rocks. Radiometric dating techniques allow geologists to determine the age of these deposits with remarkable accuracy. This historical record is essential for predicting future activity, although it does not provide an exact schedule. Preparedness for such an event requires coordination between scientists, government agencies, and the public. The Yellowstone Volcano Observatory (YVO), a partnership between the U.S. Geological Survey, the University of Utah, and the National Park Service, is at the forefront of this effort. The YVO constantly monitors the region using seismographs to detect earthquakes, GPS sensors to measure ground deformation, and satellite imagery to track changes in temperature and gas emissions. Public education is another key component. The more people understand about volcanic hazards, the better they can respond in an emergency. In the event of a large eruption, timely evacuation and sheltering could save countless lives. That means having clear communication channels, emergency alert systems, and preparedness drills for communities in at-risk areas. It is also crucial to manage expectations. The average American might think that an eruption is a sudden, Hollywood-style explosion, but in reality, there would likely be weeks, or even months, of warning signs. These could include swarms of small earthquakes, noticeable ground swelling, increased gas release, and changes in the behavior of geysers and hot springs. Such signals would trigger a massive response from federal and state authorities, including the Federal Emergency Management Agency, FEMA, the U.S. military, and state National Guards. Infrastructure planning plays a vital role. Stockpiling food, water, and medical supplies in unaffected areas could ensure that displaced populations receive immediate aid. Transportation networks would need to be ready to move millions of people quickly, while maintaining supply chains for the rest of the country. History has also provided lessons from other volcanic disasters. The 1980 eruption of Mount St. Helens in Washington state, though far smaller than a Yellowstone supereruption, demonstrated how early warnings can save lives, but also how challenging it is to convince people to evacuate. Globally, The 1815 eruption of Mount Tambora in Indonesia caused a year without a summer in the northern hemisphere, bringing crop failures and famine. These events underline the need for a coordinated response plan that considers not just the immediate destruction, but also the long-term consequences. In the end, preparedness is about balance. While the chances of a Yellowstone supereruption happening in our lifetime are extremely slim, the impact of such an event would be so severe that it demands attention. By studying the past, monitoring the present, and preparing for the future, scientists and policymakers aim to ensure that if the unthinkable ever happens, the United States will not be caught off guard. Yellowstone's story is not one of fear alone, it is also a story of resilience. The same forces that could one day reshape the continent are the ones that have given us the park's majestic landscapes and extraordinary geothermal wonders. By respecting these forces and preparing wisely, we can continue to enjoy Yellowstone's beauty while safeguarding future generations. To truly grasp the power and complexity of the Yellowstone supervolcano, we need to go beneath the surface, far beneath, into the Earth's crust and mantle, where the real engine of this geologic giant lies. The heart of Yellowstone's volcanic system is not a single, massive chamber of molten rock waiting to explode, as movies often portray. Instead, it is a multi-layered, interconnected system of partially molten rock spread over a vast area. Think of it not as a balloon ready to pop, but as a massive sponge, saturated with magma in some places, drier in others, all interconnected through a network of channels. Beneath Yellowstone, scientists have identified two primary magma reservoirs. The upper reservoir sits about 3 to 10 miles below the surface and contains a mixture of molten rock, hot crystals, and volcanic gases. It's relatively small compared to the deeper one but still stretches over 25 miles across. This upper chamber feeds the park's famous geysers, hot springs, and steam vents. Below it, between 12 and 28 miles deep, lies the much larger lower magma reservoir, which contains significantly more molten material. This deeper chamber is connected to the Earth's mantle by a massive plume of hot rock rising from depths possibly exceeding 400 miles. This mantle plume is what fuels the entire Yellowstone hotspot, a stationary heat source that the North American tectonic plate has been moving over for millions of years. As the plate drifts southwest, the plume burns through the crust, leaving a trail of ancient volcanic scars that stretches from Yellowstone all the way to the Oregon-Nevada border. Seismic tomography, a technique similar to a CAT scan but using earthquake waves instead of X-rays, has been key to mapping this hidden system. By studying how seismic waves slow down or speed up as they travel through different types of rock, scientists can visualize where molten material exists and how it's distributed. These 3D images have revealed that the magma under Yellowstone is not entirely liquid. In fact, the upper reservoir is about 5 to 15% molten, while the deeper one is only about 2–5% molten. This means there is far less eruptible magma than many fearmongering headlines suggest. The chemistry of Yellowstone's magma also plays a role in determining eruption style. Rich in silica, the magma is thick and sticky, trapping gases like water vapor, carbon dioxide, and sulfur dioxide. Over time, as pressure builds, these gases can escape violently, driving explosive eruptions. But in many cases, gas release happens gradually, powering hydrothermal activity rather than catastrophic blasts. One of the most remarkable aspects of Yellowstone's magma system is its interaction with groundwater. Rain and snowmelt seep deep into the earth, where they are superheated by the magma below. This water then rises back toward the surface, fueling the park's hydrothermal features. In extreme cases, trapped steam can cause hydrothermal explosions, smaller but still powerful blasts that create craters and throw rocks hundreds of feet. Scientists closely monitor the behavior of both magma chambers using an array of instruments. GPS stations detect ground uplift or sinking, which can indicate movement of magma or changes in underground pressure. Gas sensors measure emissions of CO, SO, and other volcanic gases, while thermal cameras track temperature shifts on the surface. Even slight variations can signal changes in the system's dynamics. There's also fascinating research into Yellowstone's deep earth connections. The mantle plume under the park is part of a much larger system that may extend into the lower mantle, possibly linked to heat anomalies beneath the Pacific Ocean. This raises big questions about the stability of mantle plumes, the lifespan of volcanic hotspots, and how they influence continental geology. Despite all this monitoring, predicting exactly when Yellowstone will erupt is not possible, and it's unlikely to happen anytime soon. The best scientific models suggest that while magma is still present and active, it is not currently in a state that would trigger a supereruption. In fact, the most probable future events are smaller hydrothermal blasts or localized lava flows, both far less destructive than Hollywood disaster scenarios. Still, the scale of Yellowstone's magma system reminds us of the immense forces at work beneath our feet. It is a living, breathing geological engine, reshaping the land slowly but powerfully, and offering a rare glimpse into the deep earth processes that have shaped our planet for billions of years. An eruption at Yellowstone, even a smaller one, wouldn't just be a local event. It would be a national crisis, and in the case of a truly massive eruption, a global one. To understand why, we have to look at the environmental and atmospheric chain reactions that such a geological event would set in motion. First, there's the ash. Volcanic ash is not soft like fireplace soot. It's made of pulverized rock and glassy shards, abrasive enough to destroy engines, clog water systems, and damage electronics. A major Yellowstone eruption could send ash high into the stratosphere, carried by jet streams across North America in a matter of days. The heaviest ash fall could blanket entire states, especially Wyoming, Montana, and Idaho, with several feet of debris, collapsing roofs, smothering crops, and cutting off transportation routes. Even cities hundreds of miles away, Denver, Minneapolis, Chicago, could see inches of ash on the ground. The damage to agriculture could be devastating. Ash can chemically alter soil, making it toxic to many crops. Combined with reduced sunlight from the atmospheric ash cloud, this could trigger food shortages in parts of the United States. Livestock would also be at risk, as grazing lands become unusable and water supplies are contaminated with acidic volcanic particles. Then there's the issue of air quality. Volcanic ash is hazardous to breathe, especially for people with asthma or other respiratory conditions. Microscopic particles can stay suspended in the air for weeks, creating a persistent health hazard even in regions far from the eruption site. During past volcanic events, cities thousands of miles away have recorded air pollution levels high enough to require masks and sheltering indoors. But the real global impact comes from the gases. A large eruption at Yellowstone could inject hundreds of millions of tons of sulfur dioxide into the stratosphere. There, it would combine with water vapor to form tiny droplets called sulfate aerosols, which reflect sunlight back into space. This process could cause global temperatures to drop by several degrees, a phenomenon known as a volcanic winter. History has shown how powerful this effect can be. The 1815 eruption of Mount Tambora in Indonesia caused the infamous year without a summer, leading to crop failures and food shortages across the northern hemisphere. Yellowstone's past supereruptions were even larger in scale, meaning the climatic consequences could last for years. Scientists estimate that such a drop in temperature could disrupt global agriculture, shift rainfall patterns, and trigger long-lasting ecological changes. The eruption would also disrupt infrastructure in ways many people don't consider. Modern society depends on air travel, but volcanic ash can cripple jet engines, forcing the closure of airports across entire continents. Electrical grids could be stressed or even fail in ash-covered regions, and internet and communication lines could be damaged or overloaded. Even oceans would feel the effect. Cooling temperatures and altered wind patterns could shift ocean currents, potentially disturbing ecosystems and fisheries thousands of miles from the eruption site. Acid rain from volcanic emissions could also harm freshwater lakes and rivers, impacting aquatic life. In the United States, the economic costs would be staggering. Billions, possibly trillions, of dollars in damage could occur from infrastructure loss, agricultural collapse, and disrupted trade. Insurance companies would face unprecedented claims, and the federal government would likely have to coordinate one of the largest disaster responses in history. Yet, it's important to emphasize, while these scenarios are scientifically plausible, they are also highly unlikely to happen in our lifetime. Yellowstone's monitoring system is among the most advanced in the world, and scientists would almost certainly detect signs of a major eruption months, if not years, in advance. That lead time could save countless lives by allowing for evacuation, stockpiling of supplies, and protective measures for infrastructure. In the end, Yellowstone is both a reminder of nature's destructive potential and a testament to the resilience of human knowledge and preparedness. Understanding the environmental and climatic impacts isn't about fear, it's about being informed, so that when nature speaks, we are ready to listen. To truly understand Yellowstone, we have to look at its past. Beneath the forests, rivers, and wildlife-filled valleys of Yellowstone National Park lies a record of incredible volcanic activity, a geological diary written in layers of rock, ash, and lava flows. Scientists have spent decades piecing together this history, and what they've found is as fascinating as it is humbling. The Yellowstone hotspot, the deep mantle plume of heat and magma that fuels the volcano, has been active for at least 16 million years. As the North American tectonic plate slowly drifted southwest over this stationary plume, a trail of ancient calderas and lava fields was left behind, stretching from Oregon through Idaho to its current position under Wyoming. This trail marks a volcanic track that tells the story of some of the most explosive eruptions in Earth's history. When people talk about Yellowstone's supervolcano, they usually focus on its three most recent supereruptions, events that were thousands of times more powerful than the 1980 eruption of Mount St. Helens. The first of these occurred about 2.08 million years ago, forming what geologists call the Huckleberry Ridge Tuff. This eruption was colossal, ejecting more than 2,500 cubic kilometers of material into the atmosphere and covering much of the western United States in ash. The resulting caldera was over 60 miles wide, a scar on the landscape that took centuries to cool. The second supereruption happened roughly 1.3 million years ago, producing the Mesa Falls Tuff. Though smaller than the first, it was still massive by any measure, expelling around 280 cubic kilometers of volcanic material. Its ash deposits can still be found in places as far away as the Midwest. The most recent, and perhaps the most famous, supereruption occurred about 631,000 years ago. This is the event that created the modern Yellowstone caldera, a massive depression measuring 30 by 45 miles. Known as the Lava Creek Tuff, this eruption blasted more than 1,000 cubic kilometers of rock and ash into the sky. The ash layer from this eruption has been detected across nearly the entire continental United States. It's important to remember, however, that Yellowstone hasn't been quiet since then. Over the last 631,000 years, it has experienced dozens of smaller eruptions, many of them producing thick lava flows rather than explosive ash clouds. The most recent lava flow, the Pitchstone Plateau, erupted about 70,000 years ago. While these smaller events wouldn't be considered super, they could still have significant local impacts. In addition to volcanic eruptions, Yellowstone's history includes enormous hydrothermal explosions, steam-driven blasts that occur when underground water is superheated by magma and then suddenly depressurizes. The largest known of these in Yellowstone happened about 13,000 years ago, leaving behind the Mary Bay crater in Yellowstone Lake. Scientists use a variety of techniques to reconstruct this timeline. Radiometric dating of volcanic rocks provides precise ages for past eruptions. Ash layers found in distant sediment cores allow researchers to map the reach of each event. Geophysical surveys reveal the shape of ancient calderas buried beneath younger lava flows. Even microscopic crystals inside volcanic rocks can hold chemical signatures that tell scientists how long magma sat underground before erupting. One thing the timeline makes clear is that Yellowstone's volcanic activity is episodic, powerful eruptions followed by long quiet periods. The gaps between the three big supereruptions are not perfectly regular. About 800,000 years between the first and second, then roughly 670,000 years before the third. Some people mistakenly think this means Yellowstone is overdue, but the Earth doesn't work like a clock. Volcanic systems erupt when conditions in the magma chamber are right, not on a fixed schedule. The historical record also shows that Yellowstone is a dynamic system, constantly evolving. Even in its quiet phases, the ground rises and falls as magma shifts below, and thousands of small earthquakes rattle the park every year. These are not signs of an imminent disaster. They are signs that Yellowstone is alive, a breathing giant in the heart of America's wilderness. Looking at Yellowstone's timeline is like reading a few pages from a book that's billions of years long. We can't see the ending, but we can learn from the chapters we have. Each eruption, each lava flow, each ash deposit adds to our understanding, and helps us prepare for whatever the next chapter may bring.